Hello, everyone. My name is Dr. Shaktiver Singha. Welcome to this rather short lecture on use of AI security tools. This will be a very brief lecture introducing to several core concepts, or you can say use cases surrounding AI for system security. And I will introduce to several AI-based tools based purposefully in line with these concepts. Nowadays, when you typically hear this title, use of AI security tools, we tend to picture a developer opening ChatGPT, pasting in a buggy function, and asking, hey, is this secure? But through this lecture, I want to point out while this thinking is obsolete, AI tools could perform a much integrated job in the software lifecycle. When you graduate and join teams at Microsoft, Google, or Amazon, they won't ask you to be a prompt engineer, but rather they will ask you to be an AI security architect. So I'm going to walk you through the 5 uses mapped to 5 stages of AI-driven security architecture, and we will look at the enterprise AI tools defining the market right now. And I will also go take alongside some of the very recent research from my lab and elsewhere as well. Let's start with the biggest failure mode of modern AI. If you paste a single Python file into GitHub Copilot and ask to create a unit test to asset authorization, it will actually generate a decent amount of test cases, mostly runnable and mostly accurate. We can also look at more research tools such as EvoSuite and EvoMaster, which are developed based on genetic algorithms to similarly produce security-related test cases. But they would be developed within a bunch of other test cases as well, which we call web fuzzing. But then you need to compare this with distributed systems. Take a look here. This is a microservice system. And over here, for context, consists of multiple independent microservices or softwares that interact really as a mesh to develop a one holistic system. So when you ask Copilot, EvoMaster, or EvoSuite about a vulnerability that may actually span across 5 different microservices in the call graph, it will actually fail. Why? Because they sees only text, not the structure that you see here. Security threats can actually be born from the semantic interactions among distributed components. Hence, when you lose system, structural, semantic context of a system, when you treat a code as text, which an LLM is trained to do, then you are actually losing a lot of information that are actually reliable and useful enough to actually deduce some of the security threats or vulnerabilities that could actually exist as grave failures within the system. This is why we see the industry shifting towards tools like Snike Deep Code AI. Unlike standard LLMs, Snike does not just read the code, it actually builds a semantic graph. Sometimes in the literature, we call them the superprogram. Similar to what is here in this graph. And there are just tools like Float, right? Just basically do this kind of super program development. Now, it looks at data flows across files and recognizes possible vulnerabilities from reasoning out the symbolic evidences. Now, symbolic evidences are nothing but signals that exist in the semantic interactions and the structure itself to imply a potential vulnerability in the system. Now, if you look at these two research tools, we also get to see that just code is insufficient to effectively uncover vulnerabilities. Now, take kernel fuzzing, for example. We see the actual memory state of the Linux kernel being embedded into the AI model that generate tests cases as a form of system context that could be used to infer runtime signals of possible vulnerabilities. So here's the important lesson. Don't just prompt for security. Try to always map the territory or the context of the system itself that could potentially produce vulnerabilities in the system. Now that the AI understands the context, we ask it to find bugs. That's the simple logical next step. But here's the danger. AI is always probabilistic. It guesses. But in security, a guess is not adequate. We need some form of mathematical certainty. Now, currently, the industry relies on formal verifications, and these are some of those tools. Think of AWS Selkova, which uses SMT solvers. I'll come back to SMT solvers later. But SMT solvers to basically prove that your cloud permissions are actually safe. And there are ways to do that. Take S3 buckets. Selkova basically verifies the correctness of the security of access control policies, such as IAM and bucket policies. Basically, rest of these tools also do something very similar. Now, satisfiability modular theories, or SMT, is a formal methods technique that determines whether a logical formula is sustainable under precise mathematical theories, and you could call them predicates. Take a simple example of an interconnected service A and B in a microservice system. For the same user, service B may be restricting, but still that user may get access to service B via service A, which has a relaxed policy now. Now this compromises B and hence the system as well. Now if you think mathematically, if we define a predicate, like if a request reaches service B, the user must possess admin privileges, we can verify through first order reasoning that this interaction is a vulnerability, right? Now, we trust these solvers implicitly. AWS trusts these solvers implicitly. Microsoft trusts these solvers implicitly for accessing and verifying the policies that are in place. But the question is, should we trust these solvers? This is where research comes in, and we asked a very scary question. What if the math tool itself is broken? If you go through a paper, we can see generative AI being used not to write security testing code, but to attack the formal rule solver, like the Microsoft Z3 itself. Now, in this paper, this found 45 critical bugs in a very foundation of the modern verification. So when you build AI for AI security pipelines, remember, you need AI to check the logic of the code, but you also need logic to check the AI as well. So you should always see that there is a very symbiotic relationship between the AI security tools that we already have. Now, phase 3 is where we stop treating AI like a black box. So right now, most developers just accept whatever security model, GPT, Val Codebert, Llama, or any LLM would give. But for security testing, a generic model will only generate mediocre tests and artifacts to identify vulnerabilities. We have done some testing to see that these sort of very generic models do generate a lot of problems that needs a lot of sanitizing and also optimization, and hence why optimization here. Now in open source, Google is actually leading the way here with tools like OSS Fuzz. And we can also find very similar tools called Cluster Fuzz, Hong Fuzz, FSL AFL And these are actually using LLMs to generate fuzz targets. Now, in fuzz targeting, AI most often are used to generate and feed large volumes of malformed, unexpected, or random inputs to a component like API, input parser, or an interface. So the idea is to discover crashes or security vulnerabilities when it's kind of been brute forced with these kind of tests. So, but how do we make those targets better? That's the problem. Now, we don't do it by just asking nicely from an LLM. We just don't do it by updating the prompts in a way that we could, improve the outcome or the tests that have been generated. So now, if you look at the recent work, this problem is approached using reinforcement learning. Now, take a PyTester project, for example. So this entire figure is about PyTester. It does not measure success by text similarity. So what I mean by text similarity, it's basically the measure that measures the similarity that manual tests would have to these sort of generated tests. But in fact, these kind of projects don't even care about how the code looks like or how pretty it is. PyTester, for example, here sets up a reward loop. Now, if the AI agent writes a test that crashes the server, what would it get? It would actually get a reward. Now, if it writes a test that fails to compile, then that means the generated code itself is buggy. So, which means the agent should actually get a penalty. Now, over thousands of iterations, the agent learns to ignore the bad habits of generating security tests and picks up from that it might have actually picked up from the internet, from a large corpus of different security test code. But then over these iterations, it would actually become more of a better vulnerability hunter. And this is, if you look at the figure here as well, you could see that this actually follows much of the process that reinforcement learning from human feedback approach to LLM tuning uses, right? Now, these sort of approaches can be very appropriate because why? You could see that systems technically evolve over time in terms of structurally semantic relationships, the dependencies they have, and so forth. So the call graphs could also evolve. And there is also an aspect where this attack vector is evolving as well with time. So optimization through this sort of feedback is actually going to be really useful in order to maintain producing these sort of security agents, AI-based security agents producing valid tests or security testing outcomes or artifacts in the long run. Now, okay, so we have a hyper-optimized AI agent generating attacks, right? Now, what happens if we accidentally deploy this agent against our production database? Or maybe think, what if the agent itself is hallucinating a library that installs a malware? For example, you could one of the best examples that I can find is Log4j. We know it carries a vulnerability, but still, given the fact Log4j has been used everywhere in most of the code, LLM still uh, could be pushing Log4j in even in test code. Then the case is this: you cannot have AI security without AI safety. Now, in the enterprise level, we are seeing the rise of tools like NVIDIA NeMo guardrails or Azure AI content safety or Open Policy Agent Rego as tools which are actually going to be this buffer between AI agents that produce security tests and the actual tests that get executed in the system itself to test out for vulnerabilities. Now, you can think of these tools as literal firewalls for AI-based security tools. They intercept the AI's output and put it in a simple way. It says that, no, you can't execute that command. It's that simple. Now, for example, again, let's take NVIDIA NeMo guardrails. Now, that defines and enforces constraints that an LLM must follow by intercepting the inputs and outputs to ensure responses follow a very specific safety policy and behavior requirements. So the rules are set. So this guardrail is checking if the LLM is following them. If it does not, it gives the feedback to the LLM that you have to be following these sort of guidelines. Now, I can give a more specific research example. Now, in our recently accepted publication, a methodology that we call AI test, we basically combine those formal logic constraints that I mentioned earlier with these sort of guardrails. So what we do is essentially for every single line of code that we generate, we verify them against the mathematical policy before it ever touches the compiler. So far, what we have seen is that it has achieved almost perfect semantic validity, right? So what's the takeaway? Trust AI security tools, but always verify them. And that's another use of AI security tools that are available there. Now, finally, we have to accept the hard truth, right? Despite graphs, our solvers, the validators, our guardrails, attackers will still find ways to go around established AI-based security enforcements. So the final tool in your toolkit should be AI tools for observability. Now, the old way was actually writing regular expression rules, which basically searches for logs, for example, with the word error. But the new way is AI native observability. Now, you could be looking at tools like Dynatrace Davis AI or Elastic AI Assistant, which are enterprise grade. But I also highly encourage looking at research level tools such as Deeplog, Diffusion, and Instant Ops, which uses advanced AI techniques to detect suspicious security anomalies as well. Now, these tools don't just search for keywords. What they do is actually casually understand the semantics of a system. So for instance, they can recognize that a 50-second delay in the payment API is statistically awkward, weird. Now, even if no errors has been logged, right? Now, we conducted a very recent systematic review that is basically very consistent with this sort of a sub-frontier. Now, we're actually moving from log parsing using regex to anomaly understanding using transformers. So that's basically our trend in terms of anomaly detection and observability using AI tools for security. So these AI tools watches the logs for potential signals of security anomalies, like the one that I mentioned before, the 50-second delay in the payment API. So the idea is, so when you use AI tools for security, like in this case, the practitioners don't have to do this manually, and often they're not. Practitioners have to resort for guesswork for these sort of problems. But when you have these sort of AI tools that does casual inferencing to recognize vulnerabilities, you don't need to do that sort of hard labor work or sort of guesswork that underlines practitioners in their current work. So let's recap. Using AI security tools is not a passive activity. It's a part of the architecture. We use graphs like Snike and state vectors like in kernel fuzzing to understand context or metadata about a system from which the security posture needs to be reasoned out. We used solvers to verify logic of security enforcers, such as authorization policies, to assess the correctness of the measures that are already in place. We used reinforcement learning, like in the case of Google's Fuzzers and PyTester, to optimize the security models that generate artifacts to test the security posture or uncover vulnerabilities in the system. And then we used guardrails tools like NeMo to sanitize artifacts generated by AI-based testers and validators, such that they produce correct and acceptable security tests within the context of the system. And finally, we used AI ops tools like Dynatrace to observe for subtle security anomalies such that they can be addressed proactively by the practitioners, or even in some cases, automated tools. Now, observations can also inform evolution in architecture, semantic relationships among dependencies, and even attack vectors. Now, this can easily inform adaptations to inferring the security context of a system. The incremental software architecture reconstruction and its validation using formal methods that we have developed in my current lab called CMET is a very good example for this, and how observability informs context expansion and validation. Hope you had a very brief glimpse of use of AI security tools in this very brief lecture. Thank you very much for joining.